Thank you, Stuart. I'm going to talk today about the proliferation of hyperspectral applications using UASs. Certainly from our perspective at Headwall, primarily a hardware supplier, there's been no shortage of inbound inquiries. Every day it seems like there's a new and exciting and challenging application you can use hyperspectral for when you mount it on a UAS. And that's a technology trend or a market-driven trend that we've seen for the last 3 years. And we find, particularly in remote sensing, there's a tremendous amount of opportunity and applications for the hyperspectral capability. And I'll spend the first chart talking a little bit about what hyperspectral is for those who aren't necessarily familiar with it. But basically, it's a spectral fingerprint of what you're looking at. And from that, you can discern a tremendous amount of useful information. And as challenging and exciting as the opportunities are, there are certainly no shortage of technical challenges to properly integrating a hyperspectral instrument onto a UAS. Our technology, and it's not the only way to do it, but is a push broom sensor technology, which basically means there needs to be relative motion between your camera and the target. And in the case of the UAS, your target is fixed on the ground, and you're using the forward motion of the aircraft to help paint out one of the spatial dimensions of the objects that you're looking at. Your sensors could have anywhere from 320 to 1600 pixels in the cross-track direction. And as you step forward or move forward, we're taking successive snapshots of that line on the ground. The energy that you collect is dispersed inside the instrument and broken into its unique spectral components, anywhere from, say, 160 spectral lines to nearly 900 spectral lines to give you some very, very fine, precise spectral information. That information is overlaid on a focal plane. And again, what you build up is this two-dimensional spatial information of the scene, but every pixel of that scene has anywhere from 160 to 900 spectral bands associated with it, and creates what's called a data cube. That information, a tremendous amount of data, you do a number of things to it in a post-processing environment. In the visual here, you show the before and after doing orthorectification, where we're using the GPS IMU data that's on the platform. You can go back and remove that line-to-line variation that's caused by pitch, yaw, or roll motion of the aircraft. Once that information is processed, not only orthorectification, but you can also do radiometric calibration and a number of other things. You then look at that spectral content, and we're showing here graphically at the top right of the screen what a V-near sensor would look like from 400 to 1,000 nanometers with different spectral content. But every object on the ground has its own unique spectral fingerprint. In the lower right, you see just representative of how vegetation might differ from soil, might differ from water. The sensors that are available in the market today go down from the UV in the 250 nanometer range, all the way up commercially to the shortwave infrared at 2500 nanometers. And depending upon your application and what you're trying to see, typically precision agriculture is going to be best serviced using the V-near sensor, while if you're looking for minerals and other geology type applications, you're going to be in the near, going up to 1700, or in the sphere up to 2500. I mentioned earlier that there's an awful lot of interest. Just a couple of quick visuals. We Headwall break up our market segments into 4 principal ones: remote sensing, advanced machine vision, government defense, and biomed. But within those segments, you have a number of subsegments. And for example, remote sensing is agriculture, mining, environmental, laboratory type work. Or in the government defense, it might be ISR or Border Patrol, drug enforcement, space type work, a number of our sensors flying in space, or using the US Treasury to measure counterfeit bills. But within those subsegments, jumping back to just the remote sensing, here's a number of applications that fall within those segments and subsegments. And this list is growing nearly on a weekly basis as people come up with creative ways of using the technology. So there's no shortage of opportunities, and the majority of our inbound inquiries from our customer base are looking for remote sensing type applications using UAVs, UASs for that purpose. We have been very successful through the years, mounting and integrating our system onto a variety of different UASs. Sometimes that's Headwall is involved in the equation. Other times we are a second or a third tier supplier and we don't necessarily know exactly the application. A perfect example of that would be the Predator in the middle of that platform, in the middle of that image. But we fly in a variety of fixed wing and rotary wing aircraft. And in fact, on Sunday in the top left corner of the screen, we flew on the service drones platform for the demo that we did out at the turf farm. So fixed wing, your applications, as you're all quite familiar with, has a unique set of characteristics. And rotary wing, you can do a number of other things. Some of the larger platforms, the longer duration platforms, whether it's the in-situ Scan Eagle or others of that ilk, or Air Puma, allow you to do a wide variety of things. Some of the smaller, more cost-effective solutions for commercial applications and some technology research will only fly for 15 or 12 minutes even, depending upon the size of the platform, the battery power, and the payload weight. Takeaway for us over the past 3 years, it's not trivial to integrate push-through line scanning on any platform, particularly on a small UAV that has a lot of the aircraft motion. So some of the considerations that we take into account when we're working with our customers, first, they'll generally come to us, hey, I already bought a UAS, what can I do with it? Or I'm considering buying a UAS. So the Q&A goes along the lines, okay, what altitude do you want to fly, what sort of range do you plan to cover, airspeed, logistics chain, portability, price, etc. Some of the things that is not Headwall's unique expertise. But knowing that information, we can then start to delve into some of the specific applications. What band do you want to operate in? What is the mission you're trying to provide here? What are you trying to see? What sort of spectral content are you looking for? And that will drive us to a UV or a linear or a V-linear or even extended linear or SWIR type solution set. Once you have settled on that, okay, what sort of field of view, how much coverage you need on the ground, how much ground resolution distance, how narrow do you need to see 2 centimeters, or is 1 meter resolution sufficient? That will drive decisions on the number of pixels in the focal plane, it will drive decisions on the optics you choose. Ultimately, frame rate is a major consideration because if you're flying low and fast, you're going to crunch out a tremendous amount of data, and can your hyperspectral system keep up with that and have the frame rate to do that low-fast mission? Or if you're flying high and slow, that gives you a little more flexibility to loiter and build up a signal-noise ratio, a slower integration time. Spatial and spectral resolution I talked about a little bit before, but those are critical considerations. And there are applications, particularly looking for gases and other chemical constituents in the atmosphere. We're having very narrow spectral resolution, say 1/10 of a nanometer is critically important, particularly precision agriculture, fluorescence is an application that comes in play. Or can you live with a much wider spectral bandwidth because, again, what is it you're looking for? What is it that your library of information that exists that you compare this to it requires? And ultimately, size, weight, and power, because that ties immediately back to how much is available on the payload on the UAS platform. To give a little bit of a visual of how that UAS demand has skewed our product development over the years, start back in the 1990s, our very first product, the Hyperspec, fairly large, 20 centimeters, combined with the electronics package, which stored all the data. You're looking at almost 8 kilograms of weight and an awful lot of power to run that system. And the box in the middle there is basically just a repackaged computer. As UASs became more available, and particularly military applications, in the 2000s we introduced the micro hyperspec. We were able to shrink the spectrometer considerably compared to the standard hyperspec system. Not without some trade-offs in performance, and the hyperspec still has is our highest performing system, is used in a number of applications still. But getting the size of that spectrometer down, getting the size of your electronics package down as well became critical. So getting it down under 3.5 kilograms and 40 watts on average power. It's a significant reduction and opened up a whole new class of platforms that we could fly on. But as the UAS market has really exploded over the last couple of years, you see more and more small, lightweight, which also translates into small payload capacity platforms. That's driven us to an all-in-one package, which we call the Nano. Weighing less than a kilogram, it has not only the optics and the spectrometer and the camera installed in it, but it also has the data acquisition electronics. So all you have to do is turn that system on and you can fly away at less than a kilogram and collect up to 2 hours of data at the nominal frame rate of, say, 100 frames per second. So responding to that market demand in the UAS market has helped us guide our product and technology roadmap. So lastly, now you've got your UAS, you've picked the hyperspectral system, and here's where the real fun stuff starts, is actually integrating a push-proof sensor onto a moving platform. Do you have sufficient payload capacity? Balance and weight, center of gravity becomes critical, particularly if you have two components in your platform, if you want to integrate this with a LiDAR, for example. Do you need a gimbal? And quite frequently find on some of these small platforms that you do need some sort of stabilization. 2-axis, not expensive, but still a requirement to get the line of sight jitter that's going to give you pristine imagery on the ground. The ability to orthorectify and take out some of that line-to-line jitter once you've got it back in the ground. What GPS IMU, how much accuracy do you need, your DEM maps, etc. The ability to store LiDAR information in the same electronics package is something that we offer. And providing all that data management and offering a solution set, a complete turnkey solution for our customers. So as an example, just on Sunday, this was a data collect we did, again, with service drones and unmanned experts. On the left side, you can see the raw data cube, no correction applied. And you look at that car, both cars in fact, you can see considerable wavy pattern on the front bumper of both due to that aircraft motion. Even though it wasn't too windy that day, there's still some residual motion you're going to see. So taking that GPS and IMU information, you can do the orthorectification. It's not perfect yet for what I was able to accomplish on my computer in the hotel room on Sunday afternoon. This will give you an idea. You still see a little bit of residual jitter in the upper vehicle there. But to give you an idea of what you can do to sort of snap that image back into place. Typically, we do a good job with roll and a little bit of pitch, but any sort of yaw type of aircraft motion becomes more challenging. But picking the right airspeed, the right frame rate, the right integration time, so you have nice, contiguous, slight overlap on your successive scans with no gaps in between it, is part of the challenge of planning for every aircraft mission, both your platform and your sensor. So that was what we did on Sunday, but time not permitting, here's some of the hyperspectral data product that you can extract from your hyperspectral sensors. And here's four examples. There's a tremendous amount of research going on right now in plant health. You can use hyperspectral to say, that plant is unhealthy, it's wilting, it needs more nitrogen, the water content isn't sufficient. But that's a lacking indicator. Being able to actually measure the chlorophyll fluorescence is sort of an advanced warning that you have a problem approaching. And if you can tackle that before it actually occurs and translates into actual damage to the plant, you're going to greatly improve your yield. And we did some work with some folks in Spain on that. Top right, and I'll have a couple more detailed slides on this, is a representative application where you can detect chemical agents and classify them. And I'll come back to that in the next slide. Lower left, some UAS data we took in northern Arizona, again showing the raw and orthorectified data, but in this particular system we integrated a Velodyne LiDAR system, and again store that information, that data on the same electronics package, but looking for a health of vegetation in a couple of plots, test plots up in that neck of the woods with one of our customers. And a last relative example here is marine object detection. The water seen on the left is full band imagery, what you can see with the human eye. Great deal of specular reflection from the sun. If you pick, however, the right spectral lines of interest and narrow that down, the ability to look past that clutter and noise and into the water, in this case, a whale. Perhaps not a big business case for detecting whales from the air, but you can very easily think of a number of commercial and military applications where seeing things underwater becomes a critical requirement and offers a tremendous amount of benefit and advantage. So going back to the chemical agent detection, this was taken at Camp Shelby, in Mississippi. The U.S. Army was doing a mission where they were using a chemical agent simulant to use different technologies to see how well it could detect it. This is a methyl salicylate. It's wintergreen, but it has the right molecular structure to simulate a number of different chemical agents. And what they did is they went out and they placed 3 samples in this village that they created to represent a typical wartime scenario. They had us fly the UAV out. We planned a path to cover the open air. We came back and we had 4 hits. And they said, that's great, you got the 3 we put out there, but you've got 1 false alarm. We pushed back a little bit, as it turns out what we ended up detecting was where they spilled the simulant when they were preparing the samples in the parking lot. So we actually were 4 for 4, the 3 that they intended us to find, the 4th one they didn't realize was going to be there. But the ability to classify that information by the unique spectral characteristics, and here's really what we have is the line in red is the lab, basically your library. And hyperspectral generally boils down to you comparing a known good sample in a library to your actual measurement. So whether you're measuring HLB infestation in oranges and citrus crops, or you're measuring bruising on cranberries, or you're looking for insect damage on strawberries, or fecal matter on turkeys in a poultry factory, you're always comparing to a baseline case. In this case, the lab measurement was in red, and you can see for the 3 detections some slight variation, but the arc here is not to have these lines perfectly overlapped. You're looking for unique characteristics. It may be the slope in a particular region, it may be the ratio between the response of 2 different spectra. It could be the overall amplitude. There's a number of different things techniques that we use in order to extract that information and ultimately automate it for the customer. So, in summary, reductions in the overall UAS and hyperspectral size, weight, and power and price have opened up many new applications for remote sensing. Integrating these specialized hyperspectral instruments aboard any aircraft, specifically UASs, is not trivial and requires some considerable technical depth and breadth. And lastly, hyperspectral imaging allows for excellent identification and discrimination, again using that spectral chemical fingerprint that might not be readily available in other technologies. Thank you very much.